Okay, I think we are good to go now. So if you remember, last week we discussed about this concept of classification, right? So what is classification? Classification, as we said, is basically it's basically defining a function f which will map us from the feature space, which we denote by this curly x, to what we called as the label space, which we denote by this curly y. Okay, so this is feature space, and this is the label space. And this label space, this is, in case of classification problem, this is a discrete space. It can be binary, that is to say 0, 1 or minus 1, 1, or it can be like usual discrete values also. Okay, now, let us start off with the simplest case of binary classification. Now, what is binary? Binary, of course, means related to two things, where there are like we are all familiar with binary numbers. So binary, what is a binary number? A number that can take two values. So similarly, what is binary classification? Binary classification is something where such a classification problem which can take only two values. So what are the values of in for a classification problem? So obviously, whatever the output of a classification is the class label. So that is to say, some element of this label space. So a binary classification will mean that the label space has only two values. Okay, so now what are these two values? The two values can be anything depending on what exactly the problem is. If it is a cat dog classification problem, then it will be like the two values are cat and dog. If it is a like a positive negative classification problem, then the two values will be positive or negative. Or like if we are trying to represent a thing as a mathematical function, then instead of having values like cat and dog, it will be useful if we have values like say 0, 1 or +1, -1. Why? Because we will f in that case will be a mathematical function which will give some number as output. So it will be good if the two class labels are mapped to those numbers. Okay, so that is about binary classification. Now, what is the type of function f that we will learn? We discussed in the last class. The nature of the function f depends on the algorithm which we are learning. Okay. So, like different algorithms can use different types of function f, and then again, whatever function we are using, that function will have certain parameters. What are those parameters? So if we denote those parameters by theta, so those parameters will have to be estimated. Their values we will not know, but we will have to estimate them using what? Using the training data. So the task of the so as we said earlier, in the any classification problem, there are two stages. One is the training stage, the other is the testing stage. What happens in a training stage? In the training stage, we have labeled data in the form xi, yi, where xi is the feature vector belonging to the feature space. That is, xi belongs to this feature space x, and yi belongs to the label space y. Okay, and then and then what happens in case of in the training stage? In the training stage, first of all, we deploy a training algo. What does the training algo do? It gives us a function f. Now, whatever function, whatever algo we are using will fix the type of function to be used, but that function will have certain parameters, which we call as theta. Okay, so how will this parameter be estimated? The parameter will be estimated with the help of the training data. training data where we know both the input as well as the output. So using those such training data, we will estimate the parameters of the function. Okay, so at the end of the training phase, we have got both a function f as well as its parameters theta. Next, we come to the testing phase. What happens in the testing phase? Now we are given only the feature vector xi, which lie in the feature space, but the true label yi that is withheld from us. So what do? We calculate or we predict the a possible value of y using this function. So we just apply the function f on this value xi. So here we denote the theta that we have learned earlier. So what we get is a predicted value. Next, what do? Next is like we have to do the evaluation of the testing. What is evaluation? Evaluation is the process in which this yi hat and yi, these two things are compared. Using what? Using a loss function. So, and smaller is if this loss function takes low value, then that means I have done a good classification. If it takes a high value, then I have done a bad classification. Okay. So this is the story of the classification in the nutshell. So today what we are going to do is we are going to consider the simplest classification algorithm, which is that is to say the simplest possible S. Okay. In fact, it is like this classification. It is so trivial that that is it's hardly actually learning an actual function f with parameters. It's something very intuitive. Okay, so first of all, let us consider a toy example. Okay. So as I said that in any classification problem, the features lie in the feature space X, like which may be a d-dimensional. And this feature space X, this can be quite complicated. It may not some dimensions of the features can be discrete valued. Some of them can be binary valued. Some of them can be real valued, etc., etc. So that is to say, we cannot really say that this X is the same as some of the mathematical space we are familiar with. It's a vector space, but it may not be like, say, the d-dimensional real space or d-dimensional complex space or anything which we usually deal with. But for the first example, let us consider a very simple situation. What a situation? First of all, d equal to 2. Okay, that means there are only 2 attributes. So, like instead of considering a large number of attributes, let us say we are considering only 2 attributes. And also this X is the real space, that is to say the R2 space. That means what? That means every element of the lying in the feature space is basically a collection of x1, x2, where both x1 and x2 is a real number. So x1 is a real number and x2 is also a real number. So let's make an even further assumption. Let's say that both x1 and x2 lie within this range of 0 to 10. Okay, so this is of course like the kind of data set we will be dealing with, like in future or even within this course will not be so simple. They will be more complicated, but just to understand the algorithm, just to get an intuition, let us assume that this is the case. So since the data set is like this, what I can is 2-dimensional real. What I can do is I can plot them on the on any 2-dimensional surface like this screen. Okay. So along this, the x-axis or the horizontal axis, I am plotting the first feature x1, along the vertical axis I am plotting the second feature x2. Fine. So so this is of course the origin, which is 0, 0. So this is like 10, means the point, this point is 10, 0. And similarly, this point is 0, 10. So we can assume that because of this criteria, all the data points which we will be dealing with, if we plot those data points on this surface, they will lie within this square region, this 10 by 10 square region. Now let us come to see what the data set or what data points we actually have. So this is a training phase. So we will have both the input, the features, as well as the corresponding levels. So first of all, the ID numbers of the data set. So let us say n equal to 10. That means 10 data points have been given to me for training. So ID will be like simply 1, 2, 3, 4 up to 10. Okay. Fine. So now for every training data point, I have X and I have Y. What is X? X in this case is a two-dimensional vector which has X1 and X2. So let me plot, write down the values of X1 here, X2 here, and Y here. So let us just assume that Y, the label space Y, it has two values, A and B. So it's a binary classification problem, as I said, so A and B. Okay? So let us say that this is an example of a feature vector, 2, 3, A. Right? So second, this is my first data point, whose first attribute is 2, second attribute is 3, and its label is A. Okay. So suppose I want to plot this point on this plane. So maybe this is my point 2. This is say point 3. And so this point is the like what we are is the point which we are talking about, the training point. So let me write this just so since I cannot indicate the label Y here, so instead of putting a point here, let me just write an A sign here. This is A. Next, second data point. Let us just say, just for an example, let's say 6, 7, 8. So let us, maybe this point is 6 and maybe this point is 7. So I plot this point 6, 7 and I write A here. Please ask questions if anything is not clear. Third point, let us say is 8.3, 1.1 D. So 8.3, maybe it is somewhere here. 1.1 will be very low, maybe here. So I put a D here. So similarly, just like this, I will have 10 points, which I am just I am not writing down the features of like all 10 points. But let us just say that if we we may have the points distributed on this space, and so I can plot them on this space somewhat like this. I have 6 points now, 7 points, 8 points, 9 points, 10 points. Okay. So note that in this, out of these 10 points which we have got, 6 of them are A and 4 of them are B. Right? Now suppose there is a new training data point. Some training data point has come. Now, so of course it will have it. Not training. A test data point has come. Okay. So since this is the first, let's say we'll have 2 test data points. So let us say that for the test data points, the labels are not going to be released right away. Instead, so only the features will be released initially, so that you can do the prediction. That labels will be released later when you do the evaluation. But for now, even before any feature has been, the test features have been given to you, have been revealed to you. Suppose you are asked to make a prediction. A new point is coming, a test point is coming. What do you think its label will be, A or B? What will be your answer? You have not seen any feature as of now. You don't know what the point is. Still, if you are asked, should it? What?
A maybe, sir.
Why do you think A?
Because its distribution is more than B. It is 60% of the training data, sir.
Exactly. So, like we can say that whenever we have a data set like this, we already have a prior distribution on the label space. Prior distribution. A prior probability distribution, which is nothing but the relative frequency of the labels. What is prior distribution? Relative frequency of the labels. This concept of prior distribution we won't use today. We will use it more in more detail at a like after maybe a couple of more weeks or maybe 3 weeks. But the concept of prior distribution is quite an interesting one. It says that if you are given a training data set, then even without seeing any feature of any testing point, the prior, like you will already have an idea about what a point, like what a test point may be. Why? Because like you know that what are the different frequencies of the different labels. So some may be like one frequency, like one label may be more frequent than the other. So in that case, you may be tempted to say that or even if you do not observe any features, if you have only this much observation, no further information, you might be tempted to say that okay, the more whatever is the most likely class or the most frequent class in the training set, that is going to be most likely in case of the test set also. Okay? Of course, that makes an assumption, a fundamental assumption that the training distribution and the testing distribution are the same. Now, that assumption may not always be correct, but for the classification to work meaningfully, that may be a reasonable assumption to make. Okay, now, anyways, forget this. We will come back to this concept of prior later. Now, suppose the point that has been given to this point that has been given to you is, let's say 7, 5.5. So this label has not been released. So now let us do as follows. Let us first of all plot the point. So this is 7 and maybe this is 5.5. So since I do not know its value, I am putting a cross here.
Sir, and this distribution is both.
Sorry? Sorry, what? Okay, see, if you are having mic issues, you can ask later. So let us say this is the point that has been given to you for testing. Okay? Remember, as of now you have not learned any model S. You just have got this training data set. Now, on the basis of this training data set, if you consider this function x, this point x, knowing that its features are 7 and 5.5. Now, if I ask you to intuitively guess whether I should have it as A or I should have it as B, what will be your answer?
A.
Why?
A.
Its neighborhood is it contains more A's.
Okay, what do you mean by neighborhood?
Like the distance between. I mean, we can consider a circle around it.
And what is the radius of the circle?
So it is like its adjacent members are mostly A. Like as we can see, the top one is A, the right one is also A, even the bottom one is A, but the left one is only B. So that is what is meant by neighborhood A. So 3/4 of its neighbors are A. So we are assuming that it's to be A.
Right, I agree. Good point. The question is, how do I define a neighborhood? That is, like you are considering these 4 points as its neighbor. So basically, you are imagining that there is a circle like this, which includes these 4 points. So on the basis of that, I am saying that A is the majority. So what is special about this circle? Why not say this circle?
So because it is the minimum distance from the that point.
Minimum distance of what from that point?
The minimum distance between the that x and the near the other one, like other units, like A. The minimum distance of this is A, and after that the minimum distance, and after that.
Okay, fine. So that's a better way of putting it. So instead of considering circles of certain radius, what you are now saying is that from this point X, what you do is you measure the distances of the other points in the training set. Okay, so you measure the distance between this X and this, and you find it, get some value. You measure from here to here, get some value. Here to here, you get some value, etc. That is all. You basically, from this point X, you measure the distance to all the points in the training set, and then you find which is the minimum distance, or rather, out of all the points in the algorithm in the training set, which one is closest, which one is nearest to the test point. Right? That's what he said. So in this case, it turns out that this point is the nearest neighbor. This is the nearest neighbor. So and now this, yes.
Sir, but if it was very close to B, for instance, but it is actually in an area that is dominated by A. So I mean, wouldn't that be a false classification?
Yes, that also may be. So so let's go step by step. So definitely that's a correct thing. But one thing which you have to remember here is that there is no algorithm which is always correct or always wrong. Rather, each algorithm has some pros and some cons. In a particular situation, the pros may outweigh the cons. In another situation, the cons may outweigh the pros. So there is so you are always welcome to find pros and cons of different algorithms. But just because an algorithm has a con does not mean that it is bad. And just because an algorithm has a pro, it does not mean it is always good. So what we are, the simplest algorithm which we considered right now. So let me show this in a new page. Just a second. So like I'm not considering those old points anymore. Let's just say that this is x1, this is x2. Like here we have a, here is a B, D, B, A, and A. Okay, 1, 2, 3, okay, 6. Okay, and let us say that this is the point which we are considering. This is the X. So what was said right now is that we consider like the nearest neighbor. So what is the nearest neighbor? Nearest neighbor is that like you calculate the distance from X to all the points to all training points. Second, sort the distances in increasing order, in ascending order. Now, what do we after that? What do you do? We are saying that use label of nearest neighbor. What is nearest neighbor? Now that point in the training set which is closest or which has the least distance from this point X, that you consider it as its nearest neighbor and use the same level as it. Okay, so what? So in this case, which is the nearest neighbor? Probably this one. So this one is A. So I predict its value to be A. So I say that X is equal to A. Fine. Now let us consider the like another point which was just mentioned. So suppose suppose we consider we are considering this point. Okay, this point. So here like here you can see that the closest, if you are considering this point, its nearest neighbor is definitely B, right? So according to this algorithm, I may classify this as B. But as someone just said that it lies in this point lies in a place where most of the where the density of A is high, but the closest point turns out to be B, right? So in that case, does it make much sense to call it as B, to classify it as B? Well, there is no real reason to say that that it should be classified as A or it should be classified as B intuitively, because like we have that depends on whatever assumptions we make on this data set. If we make an assumption like this, that there are some high density regions of A where even the unmasked points are also A, and then there are some high density regions of B like this where the unmasked points are also B. In that case, yes, what is like what was said then, it made sense that if we consider all the A's together and say build something like a convex hull, say something like this, right? We consider a convex hull using these points A, and similarly with the using these points B, we use another convex hull like this. And for any point, we see which convex hull it lies in. Like that, in this case, this point lies in the convex hull of A, but we are putting it in like it seems to be closest to this point B. like so there is a, in this case there is a conflict. But remember that like we have not made any assumption about the data set that there is a convex hull of A's and a convex hull of B's, or there is a high density region of A's, high density regions of B's, and so on. So again, I'm not saying that that you should not make such assumptions or such assumptions are wrong. We are only saying that as of now, we have not made any such assumptions. We only have got some data points about which we have not made any further assumptions. So given that we have not made any further assumptions, it does not make much, it is not much of an issue to say that because this point, this particular point, because it is closest to a B, I will call it as a B. So that's what you can do that. There is no logical inconsistency in saying it. But it may easily happen that the nearest neighbor is what we call as an outlier. What is an outlier? Outlier is a data point which is it is different from all the points. Like say for example, I will give you an example of an outlier. And that is the notion of an outlier basically comes if we are making some kind of an assumption on our data set. As I said, in this case data set, we have not made any particular assumption. But if we do make some assumptions, then the concept of outlier comes. So let us say that there is a data set like this.
Excuse me, sir.
Yes.
Sir, in this case, first we are sorting the distances in an ascending order, and the first, which is the nearest, we drive our conclusions according to that. Sir, is there a scope that we take more than one features to like drive the whole conclusion, like not only one feature, more than one feature?
See, we are not doing it on the basis of one feature. What we are doing right now is we are calculating the Euclidean distances. So so you can consider, so this is basically a problem of coordinate geometry. So there are points with each point is represented by two values, x1 and x2. So that is x1, these are the two features, x1 and x2. So when you are calculating these distances, you are calculating both the features. So let us say that this point, its features are let's say x1 comma x2, and this test point, let us say its features are let me denote them as xt1 comma xt2. This t represents test. So what I am doing is I am calculating this d as what? x1 minus x1 t whole square plus x2 minus x2 t whole square, and then the root over of the whole thing. Right? So this is the standard definition of Euclidean distances. So that's what we are calculating here, and obviously, so we are using both x1 and x2, both x1. So both features are being used here. It's not that we are doing on one feature or anything. We are doing it on both features. Now suppose there is a data set. This is the data set we are considering. Okay.
Sir, I had a doubt.
Yes.
Sir, can we like use the inverse of the distance as a weight while we are like calculating the nearest neighbor? Like more importance should be given to the neighbor which is more near.
Yes, definitely we can do that. So, so definitely that's a good point. So again, let's go step by step. So we will discuss what you said is definitely a valid idea, and we'll come to that later. But let's not jump the step. So let us look at first of all. Let us look at so as of now, what we are trying to do. We have proposed a very simple algorithm, like as simple as it gets. It can be quite naive also. Now, but what we are trying to understand now is what is wrong with it. Why is this not enough? So let us to understand that, let us first understand the concept of outlier. What is outlier? So so let us say that this is a data set which you have got. Okay, remember I have not made any assumptions on this data set. That is, I have not said that there is a high density region of A's and a high density region of B's or anything like that. This is the data set I have got. Okay. Now suppose there is a point like this in this data set which is whose features are like represented by this point, but whose label is A. Okay. Now, if you see this like data set, then you may be tempted to call this point as an outlier. Why will you say call this point as an outlier?
Because sir, most of the point A are on the left side, and the only one the A is on the right side.
Left side and right side of what?
The B, like most of the B are on the right side, and only one A is on the right side. So it is outlier.
Okay, fine. So that is one definition of outlier.
Or
But
we can consider them as clusters, sort of thing. Like, so A forms a cluster and B forms another cluster, and this A is an outlier because it is not a part of that cluster. So.
Okay, fine. That's also a definition. So there can be many ways of defining an outlier. So we have already got two ways. So first of all, you can consider a line like this, and you can say that on everything on this side of the line is A, everything on this side of the line is B, but although this point is on the B side of the line, but still it is A. That is one way. Or the second thing you said is a cluster. Let us cluster the points. We get a cluster like one cluster like this, another cluster we get like this, etc. The cluster may be like this. So this point, this lies in a cluster. This should come in a cluster of B, but we are calling it as A. Okay, so that's also a valid definition of outlier. So in general, there is no unique definition of what is an outlier. The general understanding is that an outlier is just a point whose label is not what it is expected to be. Now, how do I expect the label of a point? That may be an entirely different question. That is, we can go into lots of theories about that. But as of now, by outlier, let us just mean that a point, an abnormal point. So that is like there are just like in normal cases also. Say suppose in your class there is one person whose height is 7 feet 8 inches. So you can call that person as an outlier because he is different from everyone else. Okay, so that is, if you consider like all the points belonging to a particular class A. So this point, although it belongs to the class A, this is different from all other points of the class A. That may be another way of defining the outlier. Okay. So basically an outlier is any point or any example which is different from what it is expected to be. So now, so why am I talking about outliers in the context of nearest neighbor? The reason might be that, as someone said, that if we consider the single nearest neighbor of this test point, if we are unlucky, that single nearest neighbor may turn out to be an outlier. So, like for example, in this data set, if we are considering this point X, okay, this given the nature of the data set, we would probably think that this point should be classified as B. But its nearest neighbor is this point whose label is A. But then this point is an outlier. Okay, so but as of now, before doing an analysis, we may not know which point is an outlier and which point is not. So if we are unlucky, the nearest neighbor of this point of any point may turn out to be an outlier, in which case it will be incorrectly classified. So that is, although this point is expected to be B, but because it is closest to an outlier, so we classify it as A, just like someone said. Okay, so here what we have got is the con of nearest neighbor. Con. What is the con? nearest neighbor may be an outlier. An outlier is something which is simply an unusual point. So you generally do not classify everything considering that as the as your example. So that is so suppose it's like a freak case. It's like it's like an unconventional case based on which you should not take any decision. So like I gave an example of outlier in terms of height. Similarly, there can be outlier in case of say CGPA, or outlier in case of say the place where one lives and so on. Right. So suppose someone is trying to understand from where does a person from IIT Kharagpur, like where do the students of IIT Kharagpur stay, in which hostel? Suppose this is the question one is somehow trying to answer. That is, they have the different attributes of a person, and also along with it they have the hostel ID in which you are staying. Suppose this is a problem which you are trying to solve. Based on various attributes of students, you want to predict which hostel they stay in. It may seem a strange problem, but because the hostel allotment may be random, or I don't know how exactly hostels are allotted, but let us assume that it is random. So, but so in that case, trying to predict the hostel of a student based on other attributes may not be a great idea. But suppose it turns out that there is one student who does not live in any particular hostel, rather that student is the son or daughter of a faculty, and so that student stays in a faculty quarters. Okay. Now a test student comes and you measure the various attributes of that test student, and you find that the attributes are closest to this person who stays in the faculty quarters. So you classify that this person is also should be staying in the faculty quarters. But that will be an incorrect classification. That's likely to be a strange way of classification, because the example which you considered in this case is an outlier. I mean, 99.9% of the students live in some hostel or the other. It's only this very few students who are say the children of faculty members, so they live in faculty quarters. But so those people we can say are outliers in some sense. But you may, when the test point came, you made the prediction using an outlier as an example. So that's so we can say that that's probably a wrong way of doing a classification. So that is the problem that may arise if you depend on only one single point as the nearest neighbor. So what do? We may, as someone was suggesting earlier, we may consider a radius. We may consider a number of points, or we may consider all the points which are within that radius, and we may take the decision by taking something like a majority voting of those points within the radius. But then again, the problem arises, what should be that radius? As of now, normally we do not know what can be a meaningful value of the radius. If the point is something somewhere here, if the test point is somewhere here, and if we take a radius like this, then it will not contain any point at all. On the other hand, if a circle of the same radius is considered for a point which may lie somewhere here, I may end up getting 3 or 4 points within that radius. So what radius should I take? Or on what basis should I consider a radius? There is no easy way of answering this question. So let us not go into radius. Let us just go one step further from what we have already done. From what we have already done, if we go 1 or 2 steps further, what do you think we can do? Or how we can get around this particular problem?
So we can see the second nearest neighbor.
Exactly. Instead of focusing only on the nearest neighbor, let us consider the first two nearest neighbors. So in this case, this is like we are considering this is our as our test point. So here its nearest neighbor is this, which has label A, but our second nearest neighbor is this, which has label D. Okay, so now if I consider its nearest neighbors, I have got one A and one B. So what do I do now?
We have to take odd number.
Like so we have to take the odd number of nearest neighbor, like so that we can see the probability. Like
Okay, okay, possible. But possible, but this odd even makes sense. Please here, like in this case, it makes sense to say that we take odd number. But suppose instead of having only two labels, suppose it's a multi-class classification. That is, instead of a binary classification, let us say if suppose there are more labels possible. See, in that case, whether you take odd or even will not make much of difference. So, I'm not saying it's wrong to take odd, but any other idea?
We can consider
Sir,
the
we could
solution.
second nearest neighbor. We can
What?
take
Sorry?
at least if there are k classes, we can take k plus 1.
What you are saying is not exactly audible, but let me give another clue based on what based on what has already been taken. So suppose I decide to consider the first two nearest neighbors, first two NN. Okay? So I find that a tie has happened. Now, when I see a tie has happened, then what can I? Then obviously I have to break the tie. How can
Sir, we could always increase the radius and see if some other nearest neighbor is giving us a better result.
we can, again, we are not dealing with radii. What you probably meant
Okay,
by
so
yes, what you probably meant is that instead of considering two nearest neighbors, let us now take another neighbor, take the third nearest neighbor also. Okay, so let us say the third nearest neighbor in this case is this point. Okay, so I say A here. Okay, so now I have got two A's and one B. So I may think that at this point I may be tempted to say that or tempted to classify this point is A because A is leading by 2:1. Fine. So like I can do that. There is nothing wrong in that. So in that case, I have so what did I do? I if I take one nearest neighbor, a single nearest neighbor, then I will surely there won't be any tie. I will be able to classify the point. But if that single point is an anomaly, then I may end up making a mistake. So I do not really trust one single person, a single query point. So what I do is instead of considering one nearest neighbor, I consider two nearest neighbors. So now the problem with having two nearest neighbor is that the two nearest the two of them may belong to different classes, right? So in that case, it's like I have got a tie. So if I get a tie, I may consider the third point. That is, instead of considering two nearest neighbors, let me now consider three nearest neighbors. Okay? So that is in this case, what do I have got? Like there is no tie now. I have got 2-1. So I can classify it as 2. Okay, as we can classify it as A. Now, so now can I say that this is a good idea, or does it also have some cons?
Sir, like what if the third nearest neighbor that we have assumed A, if there might be a situation that both A and B for the third neighbor are from equal distance from X, then I think there will be an issue considering.
Okay, okay, fine. So, so you are talking about the situation where like things are at an equal distance. But remember that we are here we are dealing with real numbers, okay? And so it is so usually they will not be integers, so they will have be some real numbers. So it is extremely unlikely that the two real numbers will have exactly equal values. So let us not consider the situation of having two things at exactly equal distance. Let us assume that it may be fair to assume that the like pairwise distances are all different from each other. They may be similar but not identical. Any other
So what if the third nearest neighbor is also an outlier?
Okay, the third nearest neighbor can also be an outlier. So in that case, what would you like to do?
Then so like progressively we'll have to take more and more nearest neighbors, and then the loop will go on because any example can be an outlier.
Any example can be an outlier, true, but in general, we can expect that there are not too many outliers. An outlier by definition is something rare or something unusual. So there, like you cannot. That is, if you have considered 3 points and 2 of them are already outliers, that's an unexpected situation. You can assume that one can be an outlier, but 2 being an outlier maybe too much. So
Right.
So I see a potential.
So sir, in that case, maybe like we'll have the percentage of like there can be a fixed percentage of outliers that can be there in a d-dimensional data. In that case, we can maybe take just one more than the number of outliers examples. Like if the number of outliers are k, then we can take k plus one nearest neighbors. So that's the worst case scenario that we'll have.
Okay, fine. The problem here is that we generally will not know, or there is like given any arbitrary data set, we will not have any idea about how many outliers there can be or what can be a possible percentage of outliers or something like that. But your broader point I take your broad point is that we take a high enough value of k so that we can expect that there won't be too many outliers in that. That is, even if there are some outliers, they will be overwhelmed by the points which are not outliers. And then out of all these points, I can take the majority voting and like whichever class gets the highest number of votes, I classify accordingly. That is the
Yes, sir.
that is the interpretation I take out of your statement. Okay. So what you said right now is basically the k nearest neighbor problem. Okay. What is k nearest neighbor? The k nearest neighbor is just like nearest neighbor. Calculate distance to all the turning points. Sort distances in ascending order. Then third point is choose first k point. Okay. From this, that is, you have sorted them to like in an ascending order. Then from that sorted list, you are choosing the first k point, and fourth, take majority vote among them. Okay, so this is the k nearest neighbor algorithm. So in case of nearest neighbor, the nearest neighbor which we are considering earlier, that is can be considered as a special case of k nearest neighbor. The special case being that k equal to 1. Now if k equal to 1, the con was that the nearest neighbor may be an outlier. So we decided not to have k equal to 1, but k to have some reasonable value. Now as it was suggested, now what should be an ideal value of k? As someone suggested, that is we should have we may somehow estimate how many or what percentage of these points may be outliers, and accordingly choose a k large enough so that we do not expect too many outliers here. But as I said that you will generally not have any information like how many outliers are expected or anything like that. So you will have to intuitively choose a value of k. Now, if k is large enough, then what happens is that you may end up, suppose like all these points you end up choosing. Okay, that is to say, you instead of selecting only 3, you end up selecting 8 points. That is to make sure that there are outliers, there are very few outliers, you choose all these 8 points. So do you think that's a good idea, and if not, why?
Then the classification will be based on only the probability distribution of all the points, almost all the points.
Right. So basically, like if k is too large, then the concept of neighborhood will be lost. That is, we may end up taking reflecting the biases of the entire data set, or a very large that is a large part of the whole data set. So that is what is the basic idea of nearest neighbor? So what was the like when I asked you initially that these are the training points I have and this is the test point, this is where the feature these are the feature vectors of the test point, then suggest a value for me. Some of you spontaneously said it should be A because it is most of the points around it are A. That's a simple answer you gave without getting into details of algorithm. So what is the assumption or a tacit assumption you made behind that? The tacit assumption you made was probably that things which look similar or which have similar attributes are likely to be the same. That is, if this point and this point, they have similar attributes, means they lie close in the feature space, then they probably belong to the same class also. That is the tacit assumption we made. That is, things that like if we try to say it in plain English, it will be that things that look similar are probably similar. Okay, that is your that's the tacit assumption behind this whole idea of nearest neighbor classification. Okay, now if you consider a large value of k where you are considering lots of examples, then the first initial assumption that things that look similar, that is getting lost, because they may these 8 examples which we are considering, some of them may be quite far away from the testing point, in which case we may not be able to say that they look similar to the training point, to the testing point. So this assumption is in some cases it's no longer valid when you are trying to classify with a large value of k. So here is a con of using large k. The con of using a small k is that it may be hampered by outliers. The con of using a large k is that it may assume it may include too many points. So this assumption is no longer relevant. So then what is the answer? So small k also has a problem, large k also has a problem. So obviously we will have to look for some intermediate k which is neither small nor large. But what is intermediate? Is 3 intermediate? Is 5 intermediate?
Sir,
is 20 intermediate? Yes.
Can we take the mean of the distances?
Sir, not exactly mean, but weighted mean, like there are 10 points and we allot a value, say 1 to the nearest neighbor, then 0.9 to the second nearest neighbor, and some sort of weighted mean we do, and then maybe we get to a conclusion.
Yes, excellent idea. Excellent idea. So basically what you are suggesting is distance weighted k nearest neighbor. Okay? So we will discuss this concept a bit in a bit. So today we are already past. So tomorrow morning we will come to this. We will discuss these variants, distance weighted KNN. Okay. So we will continue this discussion tomorrow at 8 o'clock. Thank you. Thank you for participating in the discussion.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you.